Hi guys. So today we're going to do the last new thing of the semester, and that is quadratic inequalities. So we're going to look at these both graphically and we're going to solve them algebraically. So to start by drawing the graphs, this is really just going to review some things we've already done this year. So in order to graph the quadratic, we want to write it in vertex form first. Helps us see our vertex and our transformations very clearly. So in order to write this in vertex form, whatever is in front of my A needs to get factored out. So in this case, it's a negative. So I'm going to factor that negative out of just the first two terms. Then I'm going to leave a blank. The plus 5 I'm going to leave outside. Now, if I'm going to add something to this blank to figure out that number, I take the b value, I divide it by 2, and I square it. So 2 divided by 2 is 1, 1 squared is 1. Then I need to consider what I've actually done to this equation. I've added 1, but I haven't really added a positive 1. I've actually added a negative 1. So in order to keep this equation the same, I also need to add 1 to that side of my equation. And that just keeps it balanced. Well, now those three terms are a perfect square trinomial, so they factor into x plus 1 squared, and then the plus 1 and plus 5 condenses to plus 6. So now the vertex of this quadratic is negative 1, 6. Because of that negative out in front, we know it's going to open down, and we look and see how it's changed from the parent function. Well, typically from the vertex, we go right 1 up 1, right 2 up 4, and right 3 up 9. But because of that negative, we're going to go down that amount. So right 1 down 1, right 2 down 4, and right 3 down 9. And then we're going to have those same points on the other side because of that axis of symmetry. Now, before we connect the dots, though, this is when we need to consider that this is an inequality. Since it's an inequality, remember it could be a solid line or a dotted line. In this case, because it's not or equal to, it's going to be a dotted line. And then we need to consider our shading. So typically for shading, we look at above and below the graph. Now, whenever we shade, our shading is always going to be inside or outside of the parabola. But what we're going to do is look above or below the vertex to figure out which this is. Since its y is less than, we're going to look below the vertex. Since below the vertex is inside the parabola, our shading for this graph will be inside the parabola. All right, on the next one, again, we need to complete the square. So we're going to factor out that 2 from just the first two terms. The number that goes in the blank, b squared divided by, or b divided by 2 squared. So 2 divided by 2 is 1, 1 squared is 1. If I add 1 to this equation, I'm really adding 2 times 1 to that equation, which means to keep it balanced, I also need to subtract 2. Those three terms now factor into a perfect square trinomial. That factors into x minus 1 squared. And now we can graph this. Vertex is going to be at 1, negative 1, but it's been stretched from our parent function. So normally, again, that normal pattern, right 1 up 1, right 2 up 4, right 3 up 9. But because we've stretched it, I'm going to go right 1 and up 2, right 2 and up 8, right 3 up to 18 is going to be off my graph. This time it's going to be a solid line. And then we're going to look at our shading. Since this was less than, we're going to shade below. In this case, below the vertex is outside the parabola. So I'm not just shading below, I'm shading everything that's outside. But we use that to help us figure out, is it going to be inside or outside the parabola? All right, so now we're going to look at a system of inequalities. And remember, with a system of inequalities, we care about where the shading overlaps. So we're going to start with this first one. That has a vertex of 1, negative 3. It has been compressed vertically from the parent function. So instead of going right 1 up 1, I would go right 1 up a half, right 2 up 2, and right 3 up 4.5 from the vertex. And again, I'm going to go ahead and add 4/16 as well. So right 4 up 8. So from the vertex, I'm going to move those directions to get the other points on my graph. And then I'm just going to have those same points reflected on the other side of the axis of symmetry. Since this was y is greater than, it's going to be a dotted line. And I'm going to hold off on the shading, but let's go ahead and say where it would be shaded. Since it's y is greater, we're going to look above the vertex. Since above the vertex is inside the parabola, when we shade, we're going to shade inside this one. All right, the next graph has a vertex of 3, 1. It's going to open down because of that reflection, and it's also been stretched vertically. So right 1 up 2, right 2 up 8, right 3 up 18. And because it's reflected, we're going to go down. So right 1 down 2, right 2 down 8. And then we have those same points reflected. This one will also be a dotted line. Now on the purple graph, we're shading where y is less than, so below the vertex. Below the purple graph is also inside that parabola. So the overlap is going to be inside both parabolas, which is going to be just this small little region in there. Now the other thing we need to do is state possible solutions. So anything that falls in that shaded region is a possible solution. It doesn't have to be, it can't be on the line because the line is dotted, but anything in that shaded region would be a possible solution. So one possible point there is 3, 0. Now it's hard to see another clear point that falls in that region, but remember it's any point that falls in there. It doesn't have to just be nice whole numbers. So 3.1, 0 is also a solution. All right, then let's go ahead and do B. If you feel pretty comfortable with the graphing, pause the video and try this one on your own. All right, so on B, the vertex is -3, 2. It's been reflected and compressed by a factor of 1/4. So instead of right 1, up 1, I'm going to go down 1/4, down 1, down 9/4, and down 4. Now, those two are going to be kind of hard to graph just because it's not a very accurate point. So I'm just going to plot the right 2 down 1 and the right 4 down 4. And then this is going to be a solid line because it's or equal to. Then the next one has a vertex of -1, -6. And then it has not been changed in any way from the parent function besides that shift. So right 1 up 1, right 2 up 4, and right 3 up 9. And then same points on the other side. This one is going to be a dotted line because it's not or equal to. All right, on the blue graph, we're shading above the vertex. Above the vertex on the blue graph is inside the parabola. On the purple graph, we're shading above the vertex, but above the vertex on the purple graph was outside the parabola. So the overlap of outside the purple and inside the blue be this region right here. All right, so now we're going to transition to look at how to solve these algebraically. So algebraically, what we want to do first is we want to look at these equal to 0 or less than or greater than 0. The reason we want to do that is think about the type of numbers that are less than 0. Okay, all numbers that are less than 0 are negative. So this question is actually asking, when is that function negative? Well, the only place that your graph can switch from positive to negative is at an x-intercept. So what we're going to do for all these graphs is find the x-intercepts. So if we can factor, let's factor because that's the easiest way to work this out. Well, this is going to factor to x minus 4 and x plus 1. And that means my x-intercepts are 4 and -1. So what I'm going to do is I'm going to plot those on a number line. Now what I'm going to do, because my graph can only switch from positive to negative at an x-intercept, that means everything in this part of my little table over here is going to be the same sign. Everything that's in this little part is going to be the same sign, and everything in this part is going to be the same sign. So what I'm going to do is I'm going to pick some test points and just figure out if my graph will be positive or negative in that region. And this is going to create something called a sign chart. And by signs, I mean a plus or a minus. So we're going to figure out if our graph is positive or negative in each of those regions. So we're going to start by picking a number in this region. So I'm going to say like a -5. if I plug in a negative 5 for x, negative 5 minus 4 would be a negative number. If I plug in a negative 5 over here, negative 5 plus 1 is a negative number. Those two things are multiplied together, and a negative times a negative is going to equal a positive number. So what that means is that everything in this region over here is going to be a positive number. Well, now we're going to pick a test point in that middle region, like 0. Well, if I plug in 0, 0 minus 4 would be a negative number. 0 plus 1 would be a negative number. Those are multiplied together, and a negative times a positive is going to equal a negative. So everything in between negative 1 and 4 is going to be negative. All right, now we're going to pick a number in our last region, anything that's over here, so like 7. 7 minus 4 is a positive number. 7 plus 1 is a positive number, and a positive times a positive is going to be positive. So now we have our chart filled in. This graph is positive in this region and this region, and this graph is negative in this region. So now we're going to use that to answer our question. Well, the question wanted to know when this graph was negative. So to answer this in interval notation, we're just going to write where it's negative, and that is from negative 1 to 4. Because it's or equal to, we're going to use brackets. All right, let's move on to B. Same process. The first thing we got to do is set it equal to 0. Now this one then, since it's greater than 0, our answer here is going to be where it's positive, because positive numbers are greater than 0. The first step, though, is to find those x-intercepts. So let's factor. Remember, when a is greater than 1, you've got that extra step. So 2 times negative 10 is negative 20. The numbers that multiply to negative 20 and add to negative 1 are negative 5 and 1. So I'm going to rewrite that problem and split the middle into those two new terms. So now we'll take out our factor from these, which is going to be x. That leaves me with 2x minus 5. Then out of the next two, we're going to take out 2, and we're left with 2x minus 5. And then the parentheses that match is your first factor. So now what we're going to do is find our x-intercepts and mark them on our sign chart. Then we're going to pick our test points. So let's pick something to the left of negative 2, negative 12. That would be a negative times a negative, which ends up being positive. Pick a test point in the middle region, like 0. 2 times 0 minus 5 is negative. 0 plus 2 is positive. And a negative times a positive is negative. Pick the last region, something like, you can do 1,000 if you want. 1,000 times 2 minus 5 is positive. 1,000 plus 2 is positive. And a positive times a positive is a positive. So now that my sign chart's filled in, I use it to answer my question. So the answer to my question is, when was this function greater than 0? When was it positive? And the positive intervals are negative infinity to negative 2 and 5 over 2 to infinity. All right, we're going to keep going just with some similar questions. On this next one, just be careful. A lot of times people look at this and they just want to square root it, but you have to be careful with that because the square root of x squared is not just going to give us x is greater than or equal to 5. It would actually be a plus or minus x, which is going to change our answer. So let's work this the same way. So set it equal to 0, and let's factor. Well, this is a difference of squares, which means my numbers on my sign chart will be negative 5 and 5. Pick our test points. Left of negative 5, like a negative 10, that would be a negative times a negative, which is positive. Pick a number in the middle, like 0. That would be a positive times a negative, which is negative. And then pick a last test point, like 100. That would be positive and positive, which is positive. Once our sign chart's filled in, answer the original question. When is that function greater than 0? That means it wants the positives. And this graph is positive from negative infinity to negative 5, We are going to use a bracket because it's or equal to, and then it's positive from 5 to infinity. Now you may have noticed all 3 sign charts we've done so far have had the same pattern. It's been positive and then negative and then positive. And you may be wondering, is that always going to be the case? Now a lot of times it is, because think about the graph of a quadratic. If your quadratic opens up, then your graph is going to look something like that. You have your x-intercepts, your graph is positive and negative in the middle. So what would change that pattern would be something like a negative a value. Because if you have a negative a value, your graph is going to open down, which means that pattern, it would be negative, then positive, then negative. So if there's a negative a value, that would change your pattern. The other thing that could change the way it looks is if there's only one x-intercept and it's the vertex. Because then your whole graph is either all above or all below the axis. So that's another thing that could change it. But typically you're going to have that alternating pattern. You just need to consider, does this graph open up or open down? So on D, we know this graph's going to open down. Now let's go ahead and find our intercepts. So to factor, I'm going to go ahead and factor out that negative to make it a little bit easier. So I'm going to take that out of all 3 terms. We're going to find the numbers that multiply to negative 14 and add to negative 5. That's going to be negative 7 and 2. I'm going to mark those numbers on my sign chart. And I'm going to pick my test points. Now this time, I need to consider that negative that's out in front there whenever I do my little sign test. So like if I picked a negative 5, that would be a negative times negative 5 minus 7, which is negative. Then I also have negative 5 plus 2, which is again a negative. And since a negative times a negative times a negative is overall negative, that's how it works out algebraically on my sign chart. Now we also know because this graph opens down, our graph is going to look something like that, which means it's going to be negative, positive, negative. Now that our chart's filled in, we'll answer the original question. It wanted to know where it was less than 0, so it wants the negative values. It's not or equal to, so we're going to use parentheses. All right, let's move on to another one. All right, very similar here, set it equal to 0. The problem here, though, you'll notice, nothing multiplies to a negative 3 and adds to a positive 4. So we can't factor here, so we need to solve with another method. We can either do completing the square or we can do quadratic formula. We'll go ahead and do completing the square on this one. So to solve by completing the square, I'm going to leave a blank. I'm going to move the 3. The number that goes in the blank is b divided by 2 squared. The perfect square trinomial gets factored into x plus 2 squared. Square root both sides. And then subtract 2. So now I know my roots. So my x-intercepts are negative 2 minus root 7 and negative 2 plus root 7. So then I'm going to pick a test point in each of these regions. It's a little bit harder here though. So this is why if you remember that pattern, it's going to be a little bit easier for you when we get to numbers like this. It's hard to kind of find what number is in between negative 2 minus root 7 and negative 2 plus root 7. Well, on this graph, the a value was positive, so this graph's going to open up, which means it's got to be positive on the ends, and it's going to be negative in the middle. We also know we want to find where this graph was less than 0, so my answer to this question is going to be the negative values. So negative 2 minus root 7 to negative 2 plus root 7. All right, on the next one, we again cannot factor. We'll go ahead and use quadratic formula on this one, though, to find the roots. So negative b plus or minus the square root of b squared minus 4ac all over 2a. So negative 2 plus or minus the square root of negative 20 over 2. Well, the square root of negative 20 we know is going to become I root 20. But what that actually means for our graph, if you're getting imaginary solutions, on the graph of the quadratic, it means that there will be no x-intercepts. It doesn't necessarily mean there's no solution to this question, because if there's no x-intercepts, what that means is that your graph is either going to do this or your graph is going to do this. It's either going to be all above the x-axis or all below the x-axis. The difference between those is, again, the a value. If a is positive, it's going to open up, which in this case is correct. So we know our graph is going to look something like that. Well, the original question wanted to know when that was greater than or equal to 0. So when is that graph positive? Well, that graph is positive. It's above the x-axis everywhere. So even though there were no x-intercepts, our solution is negative infinity to infinity because it's telling us where that graph is above the x-axis. All right, so these last two are just extra practice, very similar to what we've been doing. So if you feel comfortable, pause the video and try these on your own. All right, on G, we'll go ahead and factor. The numbers that multiply to -3 and add to 2 are going to be 3 and -1. That means that I'm going to be looking for -3 and 1 on my sign chart. If I pick my test points or follow my pattern, it's going to be positive, negative, positive. Because it's greater than or equal to 0, my answer will be the positive intervals. So negative infinity to -3, we want to bracket because it's or equal to, then union 1 to infinity. And then the last one, in order to factor, remember, we have that extra step when a is greater than 1. We need to split up the middle and rewrite the problem. The numbers that multiply to 24 and add to 10, be careful because it has to multiply to a positive 24. Those numbers are 6 and 4. So we split the middle into those two numbers. Then out of the first two, we can take out 3x. Out of the next two, we can take out 4. That leaves us with x plus 2 as a factor and 3x plus 4 as a factor. That means that -2 and -4/3 are my zeros. -2 is smaller. Because this graph opens up, it's going to be positive, negative, positive. Now, before we write our answer, we need to be careful with the original question. The original question says 0 is greater than or equal to this expression. So really, if 0 is greater than that, we want to know when this is negative. Another way we can look at this is we can rewrite the equation. If I rewrite this equation, this is 3x squared plus 10x plus 8 is less than or equal to 0. That's the equivalent expression. So if it doesn't make sense seeing everything on the right side, you can rewrite it, but again, keep in mind which way that sign's opening. The 0 is greater. The equation is less. So since we're looking for the negative intervals here, that's going to be from -2 to -4/3. Because it's or equal, we are going to use brackets. All right, so that is the last new thing for this semester. And we will have some tests and quizzes over this, but then we'll pick back up next semester.